This video is on the volume of pyramids and their corresponding prisms. I constructed right-angled, oblique, rectangular pyramids so that I could then construct their corresponding prisms. I started constructing rectangular prisms rather than just cubes and found that I had to use pyramids and mirror images of those pyramids. I'll provide a link to the nets for the pyramids so that you can construct your own pyramids and corresponding prisms. And this is the first part of a number of parts on the volume of pyramids and prisms. I'll provide links in the description below. I hope to provide all of the materials for someone to modify for their own use. So there are links to all of the images and the text files of this script. So these are the text files. There's a link to making a cube out of 3 pyramids, deriving the formula for the volume of a pyramid using calculus. There's a folder that contains all of the images used in this video, as well as the text files, and a folder that has the nets to construct the pyramids used in this video. I have lots of notes and images for all of these constructions. At this time, I'm not sure what will be helpful. I'll make the videos and decide afterwards whether or not to upload them. So all of these prisms, these are non-integer lengths for this prism. And I went through all the calculations and wrote down the results of those calculations of the edges of the pyramids to see how these edges fold together to form their corresponding prisms. This video is just an introduction. The central idea is that the volume of a pyramid is 1/3 the volume of its corresponding prism. By corresponding prism, I mean both the pyramids and the prism have the same dimensions, length, width, and height. Although the 3 pyramids have an equal volume, they are different pyramids. Each pyramid matches each of the 3 possible bases of the prism. So 4 by 5, 3 by 4, and 3 by 5. In other words, the factors for the 3 dimensions have been rearranged, but you are still multiplying the same 3 factors. In this case, 3 times 4 times 5 units. I will get to right-angled, oblique, rectangular pyramids and pyramids and their mirror images. These are 3 identical pyramids that fold together to form a cube. A cube is the only rectangular prism that can be made from 3 identical pyramids because each of the 3 choices for the base is congruent. So the 3 pyramids and the cube. So each of these bases, this base, there's a base on the other side here, they're all congruent squares. Compare the cube to this rectangular prism that has 3 different choices for the base. This is easier to see with the 3 pyramids, 1 for each possible base. So 4 by 5 base, 3 by 5 base right here, and 3 by 4 base. This prism rests on its 3 by 5 base right here. Although you could tilt this prism forward, so then it rests on its 4 by 5 base right here. Or you could tilt it to the right, so it rests on its 3 by 4 base right here. You can begin to see the need to use right-angled, oblique, square, or rectangular pyramids. The apex is pushed over to be perpendicular with the corner or vertex of the square. So here's the apex pushed over. The apex actually is pushed back in this case, and here it's pushed over to the right to be perpendicular with these corners. This opens up space in the middle into which the pyramid can be folded to form the cube. So all this space in the middle comes open, and these pyramids can be folded up into that space to form the cube. You can see a similar open space with the rectangular pyramids used for its corresponding prism. So again, here's an open space into which these 3 pyramids can be folded to form this rectangular prism. More on this in a moment, but here you can see the apex is positioned over the vertex of a square as I scroll through the different views of the pyramid. There's the apex moving over. Now it's positioned directly over the corner of the square. Move back. Move forward again. The 3 identical pyramids and the cube is the example most often seen in an internet search. What you do not see often is constructing a right rectangular prism from 3 right-angled oblique rectangular pyramids rather than square pyramids. This first link is to a video in which the presenter has a nice physical demonstration of 3 right-angled oblique square pyramids that connect together to form a cube. He shows transforming a regular square pyramid, think Egyptian pyramids, to a right-angled oblique square pyramid by pushing layers of a regular square pyramid over to align vertically with the vertex of the square base, much like this. The second link is to a video that shows using calculus to derive the formula for the volume of a pyramid. The calculus is beyond the scope of this video, but you can see his use of layers of a pyramid that connects with the first video. The calculus is when he moves to using an infinitesimally large number of layers, which is the same as using an infinitesimally small height of each layer and integral calculus. Just look at the layers and know that the calculus allows one to derive the formula that the volume of a pyramid equals 1/3 the volume of its corresponding prism. I suggest that you print some nets, construct some pyramids, and construct corresponding prisms. It was the only way that I could understand pyramids and corresponding prisms. This is a link to the images and a PDF of those images used in this video. There are nets for you to print. I copied the nets into a separate folder. It is the best way to understand. Years ago, I put together some how-to videos on constructing geometric shapes. This is a link to a playlist of those videos. Here are some examples of the nets. Don't print these. These are too small. I'll show you the nets to print in a moment. So print, score, fold, and glue, and have fun. Here are some nets to show you the color scheme, the right angles, and some calculated lengths. Again, don't print these. There are some pages with 3 nets to a page in a few slides. I use the same scheme to color the nets throughout this series of videos. The base is always blue, the height is always green, the faces that fold up inside the prism and cannot be seen are purple and orange. This edge right here is the diagonal of the prism, and these two edges, this edge here and this edge here, are diagonals of faces. The red is the triangle adjacent to the green height around the corner of the square or rectangle base. It has the same height but can differ in length. So this height will be the same, but this length can differ. There are only 3 lengths to calculate using the Pythagorean theorem: this length, and this length. This 4th length, this length right here, can be calculated, but is also equal to this length right here. These 2 lengths, this length and this length, get glued together using this red tab right here. There are 8 right angles, but only 2 to keep track of. More on this later. So 8 right angles, only 2, this one and this one, to keep track of. The next 8 slides are nets to print. There are mirror images, connectors to use to connect the bases together. I'll show you that soon. Here are the same nets colored in. There are mirror images. And here are 4 more pages of nets with different levels of labeling and coloring. These pages have 2 copies of the same net and 1 mirror image that I use in a later video. The pyramids constructed from the nets on these 8 pages are interchangeable when constructing the cube, because a pyramid constructed from a net and a pyramid constructed from its mirror image of that net can be rotated in space to match each other. This is not true when constructing rectangular prisms from right-angled oblique rectangular pyramids. You have to use both nets and mirror images of those nets. This is the subject of later videos. I use 4 prisms and their related pyramids throughout these videos. A square face right here, 2 by 2 with 3 units in height. A cube, all the edges are 3 units. A square face 3 by 3 is on its side here with a height of 2 units this way. And a prism with no square faces, so it's 3 by 4 by 5. I also made a 5th prism with non-integer lengths, just to test my thinking on drawing the nets and constructing the pyramids and constructing the prisms. There's a net for each base with the 3rd dimension drawn as the height of the pyramid. So this is pyramid 2 right here. It is 5 10/100ths by 7 38/100ths. With a height of 2 25/100ths. Pyramid 1R, and the R means reflection or mirror image, is 5 10/100ths by 2 25/100ths, with a height of 7 38/100ths this way. And pyramid 3R is 7 38/100ths by 2 25/100ths, with a height of 5 10/100ths this way. These values are calculations of the diagonal of each face. Here are the 4 prisms and their corresponding pyramids. I rotated the prisms before drawing them because it's easier to see the dimensions against the blue background. Later on, I keep the prisms in the orientation that they are folded into so that you can follow the colored faces as the prism is constructed. I want to take some time to show how the volume of these prisms is related to each other. So this is the first pair right here. This is the next pair right here, and the last pair are these 2 prisms. And then this last prism is compared to the second prism, and finally this last prism right here is compared to this first prism. This is good practice on fractional amounts and how much is needed of a fractional amount to fill a larger prism. In this first pair, the first prism is 12 cubic units, and the second prism is 18 cubic units. They both have the same length, 3 units, and the same height, 2 units. But their widths differ. The first is 2 units, and the second is 3 units wide. So the first width is 2/3 the second width. 1/3, 2/3, 1/3, 2/3, 3/3. Calculate the volume of the first prism using the dimensions of the second prism. So calculate the volume of this first prism using the dimensions of this second prism. So 3 times 2/3 of 3, this is the width, times 2 is equal to 3 times 2 times 2. That's this calculation right here, which equals the 12 cubic units. And you can check this calculation by calculating 2/3 of 18, which is equal to 12. So it makes sense. This is the same as 2/3 times 3 times 6, which equals 2 times 6, which equals 12. Or 18 divided by 3 is 6. 2 times 6 is equal to 12. A couple different ways. In the second pair, the prism on the right is 18 cubic units. It is the same second prism in the previous pair, 3 by 3 by 2. And the second prism is a cube, 27 cubic units, 3 by 3 by 3. They both have the same length, 3 units, and the same width, 3 units, but their heights differ. The first is 2 units, and the second is 3 units high. So the first height is 2/3 the second height. In this comparison, we can look at horizontal layers. 2 layers, 1, 2, compared to 3 layers, 1, 2, 3. So this is 2/3 of this height. So 1/3, 2/3, 3/3. Calculate the volume of the first prism using the dimensions of the second prism. So this is 3 times 3, and this height is 2/3 of 3. So that equals 3 times 3 times 2. So 2/3 of 3 is 2, and altogether that equals 18 cubic units. And you can check this calculation by calculating 2/3 of 27. So this is the same as 2/3 times 3 times 9. And 2/3 of 3 is 2, and 2 times 9 here is 18. Another way is 27 divided by 3 is 9. 2 times 9 is 18. In this last pair, the prism on the right is the same cube as the previous pair, 3 by 3 by 3, 27 cubic units. The second prism has no square faces and differs from the cube in 2 dimensions. 5 units compared to 3 units. The width in both is 3 units, but the height is 4 units compared to 3 units. And this equals 60 cubic units compared to 27 cubic units. They have different lengths, 3 and 5 units, 3 and 5 units, the same width, 3 units, and different heights, 3 units and 4 units. So the first length is 3/5 of the second length, and the first height is 3/4 of the second height. In this comparison, we can look at unit cubes filling each space. So 3/5, this is 1, 2, 3 out of 5, 3 out of 5, times 3/3, this is 1, 2, 3 out of 3, 1, 2, 3, times 3/4. So this height is 1, 2, 3 out of 4 units. So this is 1, 2, 3, 4 units. So 3 out of these 4 units. So once again, calculate the volume of the cube using the dimensions of the second prism. So this is 3/5 of 5 times 3, which is the width, times 3/4 of 4, which is the height. So that equals 3 times 3 times 3 equals 27 cubic units. So you can check this by calculating 9/20 of 60. So the 9/20 is this 3/5 times this 3/4. So that equals 9/20. And so 9/20 of 60. 3 times 4 times 5. So 9/20 of 60, or 5 times 3 times 4. So 9/20 of 60. 60 divided by 20 is 3. 9 times 3 is 27. Here are the calculations on a single page. The first pair is right here. The second pair is right here. And the third pair is right here. Now I want to compare this last prism on the left with the second prism from the right, and separately this last prism on the left with this first prism on the right. Both of these prisms, this prism here and this prism here, are fractional amounts of this larger prism. So I want to figure out how many of these 18 cubic unit prisms fit into this larger prism, and separately how many of these 12 cubic unit prisms fit into this larger prism. So multiples of this prism and multiples of this prism, each fitting into this cubic unit prism. This 18 cubic unit prism is 3/10 of this 60 cubic unit prism. It's 18 60ths, or 18 out of 60, which equals 3/10. This is the simplest way to look at the fractional amount. But there is a cube in between these two prisms. So if you look back at these four prisms, there's this cube right here that's in between. So if you connect this calculation to this calculation going from here to here, but do it in steps, go from this 18 cubic units to 27 cubic units to 60 cubic units, then you can build the relationship between the 18 cubic units and the 60 cubic units. As we saw earlier, the cube is 9/20ths. So this is the 60 cubic unit prism right here. The cube is 9/20ths of this 60 cubic units. And that equals the cube, 3 times 3 times 3. And this 18 cubic unit prism is 2/3 of the cube. So 2/3 of 3 times 3 times 3 equals this prism, 2 times 3 times 3. Put them together. So 9/20ths of 2/3 of 60. Well, 9/20ths times 2/3 is 3/10, and we saw that earlier. 3/10 of this prism is equal to this 18 cubic units. 3/10 times 5 is the same as 3/2. So you're left with 3/2 of 12. 3/2 of 12 is equal to 18. So these 2's cancel. You're left with 3 times 3 times 2. 3 times 3 times 2, which equals 18. Now, once we know that this prism is 3/10 of this larger prism, we know how many it takes of this prism to fill this 60 cubic unit prism, and that is the reciprocal of 3/10. That's this 10/3. So 10/3 times 3/10 is equal to 1. These 3's cancel, these 10's cancel. So 10/3 times 3/10 is 1 times the 60 cubic units. It makes this prism whole. It gives you the entire 60 cubic units. So 3 1/3 of these prisms will fit into here. The pale pink prism is 3 by 3 by 2. It is this smaller prism right here, which is one of the 18 cubic unit prisms. The orange is a second, and the hot pink right here, is flipped on its side, is a third. This small red prism is 1/3 of 18 cubic units. So you can flip this on its side and slide it into place right here. And you can just count, confirm that it's 6 cubic units. It's 1, 2, 3, and this bottom layer is another 4, 5, 6 cubic units. So 3 1/3 of these prisms is equal to 60 cubic units. Well, 3 times 18 is 54, and 54 plus 6, 1/3 of 18 is equal to 6. So 54 plus 6 will get you to the 60 cubic units. This is tough thinking. It takes a while to see and understand the calculations and the relationships. Looking at a second example might help. Once again, the simplest calculation is 12/60ths. So this is the smallest prism that's on the right. It is 12/60ths of this larger prism. 12/60ths simplifies to 1/5. 2 times 6, and 2 times 6 times 5. The 2 times 6 are 12, the 2 times 6 are 12 cancel, and you're left with 1/5. But as before, step through these 4 prisms. So calculate the fraction of this prism, then calculate the fraction of this prism, then calculate the fraction of this largest prism. So 9/20ths of this larger prism is the cube, 3 times 3 times 3, we saw before. 2/3 of that cube was the 18 cubic unit prism, which is 2 times 3 times 3. So remember, these 3's cancel, and you're left with 2 times 3 times 3. And 2/3 of that prism, the second prism from the right, is 12 cubic units. So again, these 3's cancel here, and you're left with 2 times 2 times 3. So 2/3 of 2/3 of 9/20ths of this 60 cubic units is equal to 1/5 of 60 cubic units. So this simplifies to 1/5. These 9's cancel out. 4/20ths. 4/20 times 5 times 3 times 4. You end up with 4 times 3. So 5 times 4 is 20. That cancels with this 20, and you're left with 4 times 3, which is 12. So 1/5 of that 60 cubic units is equal to 12 cubic units. Because this smaller prism is 1/5 of this larger prism, the multiplicative inverse of 1/5 is 5. So 5 of these smaller prisms will fit into this larger prism. So the purple is 2 by 3 by 2 cubic units. The hot pink is 2 by 3 by 2 cubic units. The pale pink is 2 units by 3 units, goes into the cube this way, by 2 units. And the orange is 2 by 3 by 2 cubic units. The red, 1 unit this way by 3 units this way. Remember, the height of this prism is 4 by 4 units this way. So you can think of it as cutting this smaller prism in half and stacking these two layers on top of each other and sliding them into place here. Here's a little bit on right-angled, oblique, square, or rectangular pyramids and how I make these images. I mentioned right-angled, oblique, square pyramids earlier in that they open up space in the middle in which the pyramids can be folded to form the cube. So this is a right-angled, oblique, square pyramid shoved over just a little bit so you can see all 4 faces. And the apex lines up with one corner of the base, which opens up all the space in the middle into which the pyramids can be folded to form the cube. In this figure, the top image is a right square pyramid in which the apex or very top of the pyramid is perpendicular to the center of the square or base. This is called the centroid right here. When the apex is moving from being perpendicular to the centroid, the pyramid is now an oblique pyramid. So anywhere other than perpendicular to the centroid, this pyramid becomes an oblique square pyramid, in this case, a square base. The pyramids used to construct the prisms are unique in that the apex has been moved over to be perpendicular with this corner of the base. These slides are images of a pyramid that I constructed out of cardstock. In this series, I'm moving the camera over the apex and lining the apex up with the vertex of the square to show that it is perpendicular to the vertex. The side view shows the right angle of one of the faces. So this is the right angle right here of one of the faces. So these are drawings of those same photos. This image shows 4 of the 8 right angles that are in the net for this pyramid. 1, 2, 3, 4. Here are those same 4 right angles. 1, 2, 3, 4. The red and the green faces included 90-degree angles that wrap around the corner of the pyramid. So the red and green faces that have 90-degree angles that wrap around the corner of this pyramid. These are vertical faces with the apex of the pyramid perpendicular to the corner of the base. So here's the apex. It is perpendicular to this corner. It's straight up and down. So both of these red and green faces are triangles that are adjacent to 90-degree angles in the purple and orange triangles. So these are triangles that are adjacent to 90-degree angles in the purple and orange triangles. A side of each of these triangles, purple and orange, so the side right here and this side right here, connects to the apex of the pyramid. Both the purple and orange faces fold up inside the prism in which their adjacent side, this adjacent side right here, forms the diagonal of the prism. These adjacent sides to the red and green triangles form diagonals of faces. These become diagonals of faces. This edge right here, this adjacent side, becomes a diagonal of the prism. So this is internal, inside the prism. And these are diagonals of faces. These are on the outside of the prism. These two side views, together with these top views, show that the orange face has a right angle So there's that right angle right there. The orange face has a right angle that is not perpendicular with the ground. It's slanted, it's tilted, as this side extends up to the apex. On the other hand, the green face does have a right angle that is vertical or perpendicular to the ground. So this green face is perpendicular to the ground, vertical to the ground. This is a right angle at the corner. This apex is positioned directly over this corner. This is also a right angle, but it's not perpendicular to the ground. It's slanted as this side once again extends up to the apex. These right angles, here are the 4 right angles right here, 1, 2, 3, 4. These right angles are used to calculate the side lengths of the triangles in the nets. So these 3 lengths, and this length are calculated, and this 4th length matches this length right here. You can calculate it, but it's the same as this length. I traced photos of constructed pyramids and prisms used throughout these videos. Here are 7 groups of 3 slides that show the photo, the traced image, and the photo together, and finally just the traced image. These slides show the 3 pyramids folding up to form the prism. The background was removed using a tool on my MacBook Pro. I then traced the photo using CorelDRAW, and finally I deleted the photo, leaving the traced image. Here are just the traced images that show the same folding to form the prism. You can see that the open space formed by the right-angled oblique rectangular pyramids is filling in as the prism forms. There is an optical illusion which makes seeing the prism difficult, so I lightened the faces and darken the edges of the prism to make it easier to see. Compare these 2 traced images, this one and this one. One is flat, not folded at all, this one, and the second is slightly folded and beginning to form the prism. These 2 views together show the apex moved to a point perpendicular to the vertex or corner of the base. Here, this apex is perpendicular to this corner, this apex is perpendicular to this corner, and this apex is perpendicular to this corner right here. This last image is a reminder that right-angled oblique rectangular pyramids of equal volume are used throughout these videos to construct rectangular prisms and demonstrate that the volume of the pyramid, so the volume of this pyramid right here, is 1/3 the volume of its corresponding prism. In this case, that prism is a cube.